Right, so what we have here is just a picture of the Kenya TART, which I took off a blog post. Um, and the purpose of this calibration is to get the antenna positions very accurate. And so what you guys have been doing is recording this spreadsheet, which is, I know it's a lot of work, so thanks for doing that. I'm sure you have sore muscles after making many measurements. Um, And I'll explain why these measurements are made and then explain how we process them to work out exactly where the antennas are. So if we go back to one of the TART viewers, here is the current view from the Kenya TART. And you can see we've got antenna positions in here, which I suspect are not correct. If we go to our original install, there's one piece of information that we use to calculate the global orientation of the array. And we use a photograph taken along the center of the array to one of the antennas to a distant landmark. In this case, the distant landmark is this building here. This is the antenna number 4, starting at 0. So here is antenna 0, 1, 2, 3, and 4. And I have taken the GPS position of the TART, which is this latitude and longitude, the GPS position of this building, taken from Google Maps, and then we can work out that the actual geographic angle of that is minus 76 degrees. So that tells us that antenna 4 is oriented at minus 76.99, so maybe minus 77 degrees. So is that clear? So can you guys hear me? Your microphones are off.
Yes, yes, you can hear. Sorry, I
So
was
yeah,
going to ask, the degrees are in relation to the center?
no, the degrees are
Yes.
in
Yeah.
relation to north. So what we look at is
Oh, to north,
yeah,
yes,
so we're
yes.
trying to find out the angle between the antenna 4, the line between the center and antenna 4, what geographic angle that is. And so this works it
Okay,
out to
okay.
be minus 77 degrees, roughly.
This is from
So
what we had during the training?
yes, so this is a photograph
Okay.
taken from the center towards one of the antennas. It can be any distant landmark. So if you could line up another antenna with a different building, that would be fine as well. This gets this this measurement gets improved with further calibration, but we use this to determine the orientation of the array. So now I'm going to get to the measurements that were made from the spreadsheet. So these measurements, there are two sets of measurements. The first one is the measurements from the center to each one of the antennas. And it's quite important that these measurements are made to the center of each antenna, if that makes sense. Um,
Yes, yes.
and so then also the other measurements are in this matrix. Let me try to, this matrix which you guys filled in. Forgive me, I don't have a mouse on my computer. So these measurements represent the measurements between pairs of antennas. And so the spreadsheet is going to read in both sets of data, and I'll show you the spreadsheet here. I can upload this spreadsheet for you. And so what the spreadsheet is going to do is going to read in the data. So here is reading in the measurements, and the radius data is on column 0, and these are the radius measurements. Then I'm going to skip these next bits because what each of these bits is going to do is bring in the other data from the spreadsheet. So here is an array of the other data. When a cell is not filled in, it gets the value of not a number, which is fine. So So that bit of code reads in the spreadsheets. And then what we're going to do is we're going to start with an initial guess of the antenna positions. And that we're going to read from the design file that was sent to you. And I've plotted those initial positions here. So this is the initial design file. Antenna 0 was here, 1, 2, 3, 4. And you can see that in the original design file, antenna 0 pointed north. So our array, the Kenya array, is rotated so that antenna 4 points north. That's not a problem. And then what we're going to do is we're going to set up, so these are the initial coordinates in millimeters. Then we're going to set up a least squares optimization. So if I chose a random set of antenna positions, for that set of antenna positions, I could compute how far they were from the origin, that is the radius numbers. I could calculate the distance between pairs of them. And from those random positions, I could calculate a score, how close they were to the measured position. So for a random set of positions, I would calculate all the measurements I had and then compare them against the actual measurements. So are you following me so far?
Yes.
Yes, yes.
Okay, great. So in order to, so I can make those pairs very easily. So I've got some code for doing that. There's some code for measuring the distance between 2 points, and a code for returning the position of the nth antenna. And what this does is, I'm going to scroll down to the bottom of this code because it's not too important. I'm going to make up a function, just a single function, which is of a variable x. And this variable x is the set of all the antenna positions. So there are 24 antennas, so there are 48 positions. So x has 48 numbers in it. And I can calculate what is called the residual, which is the difference between measured and predicted radiuses, the radius residual. So for a set of antennas of antenna positions x, I can calculate their radiuses and the difference between the measured radiuses and the ones from x. And I square that difference. And then I add to that the sum of the pairwise differences. So that is the differences of the antenna between pairs of antennas. And I can add all those up after I've squared them. And I've also got one here, which is called the rotation residual, which is not too important. So we'll leave that for the moment. It just says how different the rotation residual says, I know antenna 4, which is the global rotation index, has a certain angle. So up here, I've put antenna 4 has a global rotation degrees, and I've got it wrong here. It is meant to be minus 77. So anyhow, it doesn't matter too much because I've commented out so this is this function here, it's called the criteria for optimality. So if the positions are close to the true positions, then these residuals will be small numbers because the predicted measurements will match the actual measurements. If my positions x are far away from the true positions, then these residuals will be large numbers. And here I've taken my initial guess. My initial guess was the design file, and I've said, okay, taken my initial guess, how close are the true positions to the what is the value of this function? And I get something like, I think this is 12 million. So that means the positions are very far away from my initial guess, which is not unexpected because, remember these are measured in millimeters and they're squared, so you'll get big numbers. And then all we do is we minimize the function f. We find the set of antenna positions, which gives you the smallest value of f. That means it most closely matches the measurement. So if we do that, we've got some errors here, which is a sign that there were potential problems, but we do get a smaller value of the function. It goes down from 12 million down to 10 million. So that's the first sign that things are not so good, because typically the value in the previous cases, it started at 7 million and went down to 50. So there was a dramatic reduction. So it means that we've got some issue with the measurement. But we can do better than that. We can actually also find out which measurements contribute the most to the value of this function. And so I'm going to show you what it came up with. So here is the initial position in blue. And then here is the final position in orange. And you can see they've all been shifted a bit, which is not too surprising. There's some changes here, but antennas 13 and 14 are close. Most antennas are reasonably close. And if I calculate, I can plot all the differences and we get a scatter plot showing that antenna 12 seems a long way from initial position, as does 23, 17, and so forth. And I can plot, for example, the radius residuals. So the difference between the measured and the actual position of antenna 0 is 87 millimeters. Of antenna 12, it's 133 millimeters. And antenna 23, it's, well, negative 112 millimeters. So that says that the antenna 23, antenna 12, and antenna 0 are contributing large amounts to the difference between the initial guesses and the actual values. And I can show a histogram. Now, what's interesting is I can also do this with the pairwise measurements. So here are the pairwise measurements that are the top 5% of contributing to residuals. And you can see the measurement between antenna 12 and antenna 0 is nearly 1,000 millimeters different from what we expected. And antenna 0 and 12 is obviously the same because they're symmetric. And then the next big one will be 5 and 18, which gives us 910 millimeters, and then they get rapidly smaller. So what I suspect is that some of these measurements have had a mistake in it. It could well be that antenna 12 and 0, for example, which is antenna 0 and antenna 12, this one here, it's got 136 millimeters as the difference, which is very unlikely to be true because the discs for the antennas are that's really would mean that the antenna 0 and antenna 12 would be almost touching each other. So does that make sense? So the residual for antenna
Yes,
12
yes.
and 0 indicates that there may be a problem with that measurement. And so
yeah, maybe yeah.
So I can send you these if you would like. And if you could
Okay.
possibly make careful remeasurements of these pairs. You notice they occur twice. Each one occurs twice. So there's but the smallest of these is out by 100 millimeters. So it's likely that for the ones that are near a meter, my suspicion is that this was actually 1136. And another one was
Yeah.
5 and 18, which would be antenna 5 and antenna 18. My suspicion is that was maybe, it says 997, but maybe 5 and 18 is 1.9 meters. So if we go here to the TART viewer, antenna 5, antenna 18 is up here, and antenna 5 is there. So it should be close to 2 meters. if that makes
Yes.
sense. So
Yeah.
so that's why I'm suspecting there's some errors in these measurements. Now I can modify this to be, forgive me, I can make this, I can make it more than the top 95%. I could make it I could make it, say, the 90th percentile, and I could rerun it and get a larger list of possible errors. And if I do that, we can have a look. So here are the 90th percentile measurements, and you can see that they all get quite small, but there are a couple of big ones which might be out by a meter or so. Like 11 and 4 is apparently 500 millimeters out. And 2 and 18 is
Um,
353.
they are positive and negative numbers. So
Negative would mean that the reading is shorter than the true value, and positive would mean
okay,
then the value should be, and positive means the reading is larger than it
is
should be.
two.
Yeah. So, but
Okay.
either I suspect that the large positive ones are where it's out by 1 meter. So 17 and 9, 18 and 5. So if you could check the large ones, and I'll go,
Mhm.
and I'm going to go, just going to make it so that it doesn't print out. It only prints out one side of each pair. And I'll bring this back to 95 because I don't think it's going to make much difference. There are a few mistakes. I think these are most likely to be the big mistakes, the ones which are large numbers here.